Welcome back to the Deep Dive. Today we're digging into some really fresh research, looking at the big question around these new AI models, specifically GPT-5. Can they actually discover new math?
Yeah, it's a fascinating question. We know they're great at tests, right? Like high school math Olympiads, IMO stuff.
Exactly. But that's mostly applying things we already know, solving problems using existing techniques. Our sources today are asking something much harder. Can GPT-5 pass what they're calling the Gödel test?
Mm-hmm. And the Gödel test here isn't about, reciting theorems. It's about generating correct proofs for simple but crucially previously unsolved conjectures in really specialized areas.
So actual discovery, not just calculation.
Precisely. If AI can do that reliably, it changes the game. It becomes less of a tool and more of a, well, collaborator.
And we need that context because, let's be honest, earlier models weren't there. You remember Terence Tao's comment about an older model?
Oh, yeah, the Fields medalist. He said it was like advising a mediocre but not completely incompetent graduate student.
Right.
Right.
Which is okay, but not revolutionary.
Hmm.
So the bar for GPT-5 is much higher. Can it act like a genuinely competent researcher? That's what we need to see for real progress.
Absolutely. So the mission for this deep dive is to look at how GPT-5 did on 5 very specific brand new conjectures. These are all from combinatorial optimization, specifically submodular maximization. Pretty technical stuff.
And the setup was key.
Yeah.
The model only got minimal context, maybe 1 or 2 source papers for each problem. No training on the actual answers.
Yeah, it's a clean test.
So we're going to see where it shines and maybe more importantly, where it hits a wall. Okay, let's unpack this. First up, the wins, because there were some clear successes. The big takeaway seems to be that GPT-5 did really well, almost perfect proofs on 3 out of the 5 problems.
Right. And the common thread, these were problems where a single complex but sort of linear path of reasoning was enough.
Advanced application, maybe not pure discovery, but still impressive.
Definitely impressive. Take problem 1. It was about maximizing the sum of DR submodular functions. Now, for listeners, DR submodular functions are basically math models for things like resource allocation, where you get diminishing returns. Adding more helps less and less.
And the task was to find specific values, these coefficients, alpha and beta, to bound how well an algorithm performs.
And GPT-5 just nailed it. It took an existing proof method, the measured greedy Frank-Wolf algorithm, and correctly adapted it to find the target values. Alpha was 1 minus 1 over E. Beta was 1 over E. That shows it can handle high-level proof adaptation.
Okay, but here's a really interesting detail from the source material. The researchers described the adaptation as lazy.
Lazy. What did they mean by that?
Well, it seems the model skipped steps that were exactly the same as in the reference paper. And it stuck really close to the original proof structure instead of maybe finding a more elegant way. It basically did the minimum work needed.
Huh. That's interesting. Almost human-like in a way, like minimizing cognitive effort.
Yeah, maybe. But it does raise questions. Is that laziness just efficient processing, or does it hide a lack of deeper understanding? If it just copies chunks, how much did it really synthesize?
That's a good point. It makes verifying the proof harder for a human, potentially. You don't see the full chain of reasoning generated by the model.
Exactly. Like
Yeah.
an overworked grad student copying paragraphs to save time. We don't know yet if it's a limitation or just how it works best with current prompting. But then, here's where it gets really interesting. Moving beyond just adaptation. Problem 2. This was by criteria maximization over a p-system constraint.
Right. And the researchers had their own idea, their own conjecture about the approximation guarantee you could get.
The human guess was this pair. 1 epsilon, ceiling of log base p plus 1 of 1 epsilon.
But GPT-5 came back with something different. It proved a guarantee involving beta approximately equal to log base 1 plus 1p of 1 epsilon.
Wait, hold on. So they asked it to prove conjecture A, and it came back proving result B.
Exactly. And here's the kicker. The researchers looked at GPT-5's result and basically said, that actually makes more sense.
No way. Why?
Because logically, this infeasibility ratio, how far off the ideal you are, should get worse, should increase, as this constraint parameter p gets bigger. GPT-5's results showed that. The original human conjecture didn't capture that intuition quite right, even if it was mathematically plausible.
So GPT-5 didn't just solve a problem. It essentially refuted the specific human conjecture and provided a better, more intuitive answer.
Precisely. That feels like a genuine spark of something beyond just following instructions, real mathematical insight, even if maybe accidental.
That is huge. Okay, and then there was problem 3. Weakly DR submodular maximization. This one tells us a lot about prompting, right? How you ask the question.
Oh, absolutely. Initially, they just asked for the solution, the bound.
Yeah.
And GPT-5 gave back like a summary. It knew the area, but it didn't give the full detailed proof.
Okay.
But then they tweaked the prompt. They specifically asked for the full proof. And then it delivered a detailed self-contained analysis correctly proving the target 1 minus e to the minus gamma approximation ratio, up to an error term.
So the knowledge was kind of in there,
Yeah.
but it needed the right trigger.
Exactly. It suggests the capability is latent. It's in the model structure somewhere, but you need the right prompt, the right instruction to unlock it and get a complete, rigorous proof out.
Which means prompt engineering isn't just a trick, it's fundamental if you want reliable results from these things for serious math.
It really seems that way. It's part of the process now. What's fascinating here is, well, we've seen the successes on these more straightforward adaptations, but the whole thing kind of fell apart on the really tough ones, problems 4 and 5.
Right, this is where the limits really show up.
Yeah. And the big finding. The model fails when it has to synthesize, when it needs to combine ideas from different proof techniques or pull concepts from multiple papers that aren't explicitly linked. That seems to be the major hurdle right now.
Okay, so let's dig into that. Problem 4. This one needed a combination of two different concepts, monotonicity and gamma-weak submodularity.
Yeah, these are two different ways of describing how these optimization functions behave. M-monotonicity is about overall growth. Gamma-weak submodularity is about those diminishing returns again, but a weaker version. The challenge was to figure out how they interact for an algorithm's guarantee.
And GPT-5 just couldn't bridge that gap.
Pretty much failed completely. The first answers it gave just talked about the special cases like what happens if M1 or if Gamma 1. It just gave back known results for the simpler versions, avoiding the actual synthesis task.
It didn't want to do the hard work of putting them together.
Exactly. And when they pushed it, when they asked for that full proof, like in problem 3,
It got worse.
much worse. The proof it generated was, according to the researchers, just full of errors. Multiple mistakes of various significance levels, they said. It was clearly wrong, not just a small error, but fundamentally flawed. A total collapse in reasoning when synthesis was required.
Wow, okay. And problem 5 sounds even more fundamental in its failure. This was maximizing a monotone weakly submodular function, but with a matroid intersection constraint. That sounds complicated.
It is. So a matroid, you can think of it simply as a system-defining independence, like rules about which items you can select together from a set, often based on resource limits or structural constraints.
Okay.
A matroid intersection means you have two of these complex constraint systems layered on top of each other. Things get exponentially trickier.
Right.
And interestingly, GPT-5 actually suggested the right algorithm, something called random greedy. That's what the researchers were thinking too. So algorithmically, it was on the right track.
But the proof, the analysis of why it works.
That's where it broke down. Deep structural flaws. The core problem seemed to be that the model couldn't properly handle the combinatorics of dealing with two matroids at the same time.
What does that mean? Practically.
It seemed unable to understand the difference between removing one element from your potential solution versus having to remove two elements, which can happen when you're trying to satisfy two different matroid constraints simultaneously. This led it to calculate the size of the optimal set incorrectly. It just missed a fundamental consequence of the intersection.
So it understood the pieces, but not how they fit together under combined stress.
That's a good way to put it. It failed to grasp the cascade effect of the combined constraints.
And this leads to maybe the most critical point, something with huge implications for using these models in research. You mentioned the proofs for 4 and 5 look plausible at first.
Yeah, this is the scary part. They looked convincing. They had the structure, the language, the flow of a real mathematical proof.
So not obviously wrong.
Not at all. It took experts in that specific field digging in really carefully to spot the fundamental flaws. They weren't just typos. They were deep conceptual errors hidden under a veneer of competence.
That's the real danger, isn't it? A human might signal uncertainty, but the AI can generate something confidently wrong. If you were an expert reviewer, you might just accept it.
Absolutely. Relying on these models for novel, complex proofs without extremely rigorous human verification, it's not just risky. The research suggests it's potentially irresponsible right now. And if we connect this to the bigger picture, Remember that laziness in problem 1 and this sort of superficial adaptation that failed in problems 4 and 5?
Yeah.
It really hammers home that knowledge isn't just about having information. It's about understanding it deeply enough to apply it critically. The AI can mimic the appearance of understanding, but that human oversight, that critical thinking, is non-negotiable to catch these hidden fundamental errors.
Errors that could easily slip through if we're not careful.
Especially in highly specialized fields where maybe only a few people can do that deep verification.
So what does this all mean? Let's try to synthesize this for you listening. What are the takeaways? On the one hand, definite progress. GPT-5 shows much better baseline math skills than older models. It can execute complex, known techniques really well.
And we saw those sparks, right? Like in problem 2, where it actually corrected the human researcher's intuition. That's not nothing.
Definitely not nothing.
Yeah.
But the limitations are just as clear, that big one. Synthesis, combining knowledge across different areas or papers. That's where it hits the wall.
Yeah, problems 4 and 5 showed that starkly. It can follow a known path, even a complex one, but it can't yet seem to chart a new course by integrating knowledge from different maps, so to speak.
And the other big takeaway seems to be the power, the absolute necessity of good prompting.
Problem 3 was the perfect example. Asking for a summary versus a full proof yielded completely different results in terms of completeness and rigor.
So interacting with these models effectively is becoming a skill in itself. The quality of the question you ask directly impacts the quality of the answer you get, maybe even more than the model's raw power sometimes.
It seems like it. It's a partnership, and we need to learn how to be good partners in that dialogue.
So overall, the sample size here is small, just 5 problems.
Yeah.
But the pattern suggests, real progress on the routine stuff, on adaptation. Maybe GPT-5 is an early step towards that Gödel test goal.
An early step, yeah, but definitely not there yet. Those synthesis failures are significant hurdles.
Okay, let's leave you with a final thought to chew on. This one comes from problem 5, the matroid intersection one, where GPT-5 failed pretty spectacularly on the proof.
Right, the one with the fundamental combinatorial error.
Yeah. But here's the twist. The researchers noted that GPT-5's failure to produce a correct proof actually forced them to look much harder at their own original conjecture.
Ah, okay. So the AI struggle highlighted the true difficulty.
Exactly. They realized the problem was far more challenging, far more subtle than they'd initially thought, because the AI, even one as powerful as GPT-5, couldn't crack it with the standard approaches it tried.
Wow.
So the provocative question is, what does it mean for the future of math when AI's inability to solve something actually helps us, the humans, understand the true depth and difficulty of the problem itself? It's like the AI's failure becomes a discovery tool.
That flips the script, doesn't it?
Yeah.
Using failure as a diagnostic for complexity. That's really interesting.
Something to think about. We'll catch you next time for another deep dive.